G'day, g'day. Let's conclude our hydroxy compounds unit by today looking at oxidation, reduction, and esterification of alcohols. Our lesson objective: investigate and predict the products of oxidation, reduction, and esterification reactions of alcohols. Learning outcomes from the Cambridge curriculum we are addressing below. Let us pick right up where we left off with some more reactions of the alcohols. We looked at the reactions last time in the previous video. We looked at combustion, halogenation, and the reaction with sodium. To start off today, let us talk about dehydration of alcohols, which is exactly what it sounds like. Hydration to do with water. D, we're getting rid of it the same way we sort of colloquially use dehydration. Means there's a lack of water, so we're going to start with dehydration of alcohols, which is exactly that, the loss of a water molecule. So it's a kind of condensation reaction. Condensation reactions being where a small molecule is released or is lost, and in this case that small molecule is water, thus dehydration. An alcohol will be dehydrated to an alkene via a catalyst, and it looks very simply like this: alcohol to alkene plus water. And we have a catalyst, so we have our little catalyst above the arrow, not being consumed in the reaction but speeding it up. The reaction involves passing alcohol over a hot catalyst. And a catalyst is often powdered aluminium oxide, can also be porous pot or pumice. For example, let me draw a diagram to illustrate this. So if we were doing this reaction in a lab, we would need to have a boiling tube, which if I draw with a ruler, I might use my ruler, if I can find it, there it is. So we'll have a boiling tube, like that. Boiling tube because we're going to be putting some heat into it. Then we have a stopper in the top, and we have a delivery tube coming out of the stopper into a beaker of water that has an inverted measuring cylinder in it. This is more difficult with the ruler than it's probably worth, but there we go. So that's the inverted measuring cylinder. This is the beaker of water. We have our boiling tube and we have a delivery tube that goes in like that. Because what we produce is we produce the alkene, and the alkene comes out in the gaseous form. And then the water is just going to join its fellow buddies in the beaker of water. So we're going to apply heat from, say, a Bunsen burner. This marker isn't all that good. Let me swap it over. We can even use red for heat. There we go. Apply the heat to the Bunsen burner. And what we do is we apply the heat to the catalyst. So if I have my catalyst in here, whether that's the pumice or the aluminium oxide, we heat up the catalyst like so. Then we have our sample of the ethanol, in this case, if we focus on the ethanol, soaked in a cotton wool at the end there. So we can have our ethanol soaked in cotton wool. As this heats up, this is going to go into the gaseous phase. We're going to pass over the catalyst that catalyzes the reaction from the alcohol into the alkene. Then what's going to happen is the gas is going to pass through the delivery tube, and if we had this all submerged with water, as the gas gets released, it's going to displace the water, and we will see the water level start to go down as the gas pushes the water out of the measuring cylinder into the beaker. And then when the reaction is complete, we will have our final volume that we can read off of blue for water, just in case you're wondering. Our final volume of the gas, which in this case is going to be ethene, and we can determine how much we have produced from the starting amount of the ethanol. So important thing to note here is that we have the catalysis. From the ethanol we form the ethene and the water, and that's reflected here in our general equation of the dehydration of an alcohol here. Alcohol to the alkene plus the water. All right, here's a question. Can you write an equation to represent this fantastic diagram that I have just crafted where we're converting ethanol, dehydration into an alkene and water. General equation there, given ethanol, pause, see if you can come up with an answer and check it. Very simply, we get the ethanol. So if I write this up here, we start with the, make a little bit of space down the bottom here, the ethanol, CH3. Oh, actually, I might draw this out as a display diagram. Is that still in frame? Yep. CH3, CH2OH, that's the ethanol. And then we decompose that to the alkene, which is our gaseous ethene. So that's what we're collecting up there. And then we also lose the water because it's dehydrating. We're losing the H2O to go from the alcohol, which has the alkane bond between the carbon, to a double bond, which is the alkene. Excellent. And then, of course, as we do when we have a catalyst, important to include our catalyst over the arrow there, so aluminium oxide in this instance. Moving quickly on to the second type of reaction we're looking at today. Esterification of alcohol. So we're introducing a new functional group that we haven't really looked at before, and it is this ester functional group. So an ester functional group has a carbonyl, a C double bond O, and then a single bond O within the carbon hydrocarbon chain of the molecule. So if I draw one here, for example, if I draw propyl propanoate, we're going to have 3 carbons, and then we have the link there. This is the ester linkage, and then we have 3 other carbons, all the hydrogens that correspond to that, like so. So that would be propyl propanoate. All the hydrogens filled in, obviously. So you can see it's similar to a carboxylic acid, and then it's kind of similar to an alcohol, and in fact that's how we can synthesize them, the reaction between a carboxylic acid and an alcohol. Combine them and we get an ester. It looks something like this. We get the alcohol, we react it with the carboxylic acid, and equilibrium is formed. Recall that the equilibrium arrow here is implying that the reaction can go forward and backward, and that's important. We'll talk about that in just a second. And then we get water released as well. Now, also a catalyst involved, and an acid catalyst is involved here. So for example, let me draw you ethanoic acid and 1 propanol to form propyl ethanoate. So I'll start with drawing the ethanoic acid. Eth meaning 2, ethanoic acid, we have ethanoic acid like that. And then 1 propanol, we have HO, and then prop, 3 carbon chain, so CH2, CH2, CH3. So what we do is we form the esterification through the loss of water. So it's also, I suppose, a condensation reaction as well in some sort of way. So we lose the water molecule like that. We lose the hydroxy from the carboxylic acid, the hydrogen from the alcohol. And then a new bond forms between the carbon of the carbonyl and the oxygen of the alcohol. Now, this is quite a simplified sort of representation of this. We're just looking at holistically from a summary point of view. Not particularly interested in the steps and the mechanisms involved just yet. So then what happens is we get our ethanoic acid part there, and then a new bond's formed between the carbon and the alcohol, and then we get the alcohol part of the chain there, CH3, CH2, CH3. This gives us propyl ethanoate. So the propyl comes from the alcohol part of the name, the ethanoate comes from the carboxylic acid part of the name. Reaction conditions that are important here. It's heated under reflux. We've got to supply that energy. Reflux we've talked about a few times, very common technique in organic chemistry to supply energy to a reaction without losing any of your products or your reactants. We also said we need an acid catalyst here. Often concentrated sulfuric acid is what is used. This is twofold. It speeds up the rate of reaction and it also acts as a dehydrating agent, so it pushes the equilibrium further to the right, increasing our yield. And important to know that this is a reversible reaction. We got our equilibrium arrow here, so that implies that the reaction can go backwards. So the ester can react with water to form the carboxylic acid and the alcohol. This is a hydrolysis reaction. Hydro meaning water, lysis meaning breaking down. So we can break down the ester with water to reform the original carboxylic acid and the alcohol. We're going to spend a bit of time on esters in some lessons coming up. Just for now, we're just sort of going by, just in summary, in passing. But particularly these hydrolysis reactions is something we're going to spend a bit of time on coming up. So just mentioning it for now, but it won't be the last time we see it. Let's talk about these naming esters and how I came to this name. Why propylethanoate, why not ethyl propanoate? Well, because there are some rules. The first part of the name comes from the alcohol part, and that's given the alkyl name. So you change your alcohol name to the alkyl. So methanol becomes the methyl. The butanol becomes the butyl. So in this case over here, where I had propanol, the propanol part becomes the propyl. And then the second part of the name comes from the carboxylic acid. So the first part of the name comes from the alcohol, which is the part that is attached to the oxygens by the single bond. The second part of the name comes from the carboxylic acid, which has the carbonyl on it. So the carboxylic acid, it's given the carboxylate name. So propanoic acid becomes propanoate, methanoic acid becomes methanoate. So that is why this becomes propyl from the propanol, ethanoate from the ethanoic acid. So the ethanoic acid becomes the ethanoate, put them together, and that signifies this ester. And this would be different to ethyl propanoate. In that case, we would have 3 carbons on that side and 2 carbons on that side if we had the ethyl propanoate. Let's see if you can draw some molecules and also see if you can write out, like I've done here, a full esterification reaction. Can you draw the esters methyl butanoate and ethyl propanoate? I gave you a hint for that one just before. Then can you write an equation showing the esterification of ethanol and ethanoic acid using sulfuric acid catalyst? Name the ester product using these rules up there. So pause. I've got the general equation there. I've got the naming rules. See if you can work through those 2 questions and then check your answer. How do we do? So methyl butanoate. So that tells us that the butanoate is the part that came from the carboxylic acid. So that would be from the butanoic acid. So we would have 4 carbons on this side, like that. And then the methyl comes from the alcohol part. So we have the methyl on this side there. So this would be methyl, 1, 2, 3, 4, butanoate. So if we wanted to synthesize methyl butanoate, we would react methanol with butanoic acid, reflux with sulfuric acid as a catalyst. That was number 1. Number 2 was ethyl propanoate. So in this case, we got a propanoic acid chain for the propanoate, the carbonyl there, and then we had the alcohol, which was ethanol. So we would have the ethyl propanoate, CH2, CH3 on frame. Yep. So this is the opposite of the propylethanoate that we did before. We have the ethanol turns into the ethyl, propanoic acid turns into the propanoate, ethyl propanoate. Then we had to write an equation showing the esterification of ethanol and ethanoic acid. So let me do this down here. If we have ethanol, CH3, CH2, OH, and I react that with ethanoic acid, I will do it this way so we can see the 2 functional groups next to each other. Oh, I've really got to get some new pens here, eh? HO. And then what was it? Ethanoic acid. So that's going to be C and then CH3 like that. So what we're going to do is we're going to lose the water. So the hydroxyl there with the hydrogen there is going to come off, make H2O, form the new bond between the carbon and the oxygen to get the ester, which is ethyl ethanoate. So a bit of an easier one to name perhaps, because it's just going to have the same prefix in both cases. I'll have a C there and then a CH3 like that. Now again, if you draw it the other way around, totally fine, as long as you've got the ethyl ethanoate. I guess you could have 2 carbons on both of the carbon chains. Excellent, excellent, excellent. All right, let's move forward here. Esters are very useful compounds. Just in passing, here are some of the uses that they can be used for. They have very fragrant odors. If you ever do an esterification, I'm sure you'll be asked to carefully smell it. And they've got these sort of very, I mean, in the high concentration, they're quite pungent and quite full on. but there's these fruity undertones. And in fact, you can make esters that mimic natural flavors, like you might get a banana flavored ester or an apple flavored ester. So because of that, these fragrant odors, they can be used in perfumes, flavorings, cosmetics. They can also be used as solvents. They can act as monomer units to make polyesters. We've talked about polymerization with our polyalkenes. We can have polyesters. I'm sure you might have heard that word before. It's a type of plastic, more or less. Very useful compound, and they're found all over as biomolecules in biochemical systems. To conclude today, we're going to finish off by looking at some oxidation of the alcohols. Now, unlike the previous reactions we've looked at, where we will get the same product, well, we'll get the same sort of reaction irrespective of if we have the primary, secondary, or the tertiary. In the oxidation alcohols, the kind of product that we form won't be the same in all the cases. What do I mean by that? Let's just dive in. So, let's talk first about our oxidizing agents. So they can be oxidized by acidified potassium dichromate, which is potassium dichromate with, in an acid solution, upon warming. So we need to be able to identify acidified potassium dichromate as an oxidizing agent. Remember, when we're talking in organic chemistry, we're talking about oxidizing as adding oxygen atoms, okay? So we don't need to know the specific mechanisms of these reactions, but we just need to be able to identify that acidified potassium dichromate, we're thinking oxidation reaction. And then we can just represent it as we do with the bracket O as our oxidizing agent in the reaction. This is going to have a very characteristic orange color that is a result of the dichromate ions in the solution. So when it's acting as an oxidizing agent, it itself is reduced. So two pieces of terminology we've introduced before, oxidizing and reducing agents. The oxidizing agent is causing the other thing to be oxidized. It's supplying, in this case, the oxygen atom for the other reactant to take that oxygen atom. So what that means is if that's given the oxygen atom to allow the oxidizing, i.e. it's the agent for oxidizing, it itself is being reduced. Hopefully that makes sense. So what we see is when an oxidation occurs with this as the oxidizing agent, we go from this very characteristic orange color to a very characteristic green color. So this observation from the dichromate to the chromium 3 ions, this color change implies that a reaction has occurred. And it's important that we are familiar with these reactions, because you can be asked in the exam about the observations that you might see in a reaction. So we've got to know about the reaction itself, and we've also got to know about the observations, because that could be asked of us. So if we observe this color change, it implies that the oxidation of the alcohol has occurred. Now, like I said, this is dependent on if we have a primary, secondary, or a tertiary alcohol. We will get different products in different cases, or even no products, as we'll see. Primary alcohol is initially oxidized to the aldehyde. So recall that the primary alcohol has the alcohol with only one other alkyl group, and we've got 2 hydrogens there. That's our primary. So our primary alcohol is first oxidized to the aldehyde. So what happens here is we get our primary alcohol and we oxidize it, and we end up with the aldehyde. And then the R chain coming off there. Let me just draw that a bit neater. Move this arrow across a little bit. Make it nice and legible. Like that. So we're oxidizing from the alcohol, primary alcohol, to the aldehyde. And we also get some water on the end there. So if I were to draw that as a structural formula, we have our alcohol. Now again, the oxidizing agent, we just do as an O in brackets. We form the aldehyde. Notice how it's CHO. That's how we denote the aldehyde. And then the water. Now this is when we have warming. So these are relatively mild conditions. We can oxidize that even further if we heat it with reflux and with excess of the oxidizing agent. So what we'll observe then, if we have the further oxidation, is we take the aldehyde and we oxidize it more. We add an, We add an extra oxygen atom to it. That's my aldehyde. Yep. Add the extra oxygen atom to it. Oh, this is getting real bad. So we're going to be able to get through. There we go. Plus the oxygen atom like that, and we get the carboxylic acid. So this is under mild conditions. So this is just warmed without dichromate. This is refluxed with excess of the oxidizing agent. So much harsher reaction conditions, but still very easy to convert the primary alcohol through to the carboxylic acid. What about if we have the secondary alcohol? A secondary alcohol will be oxidized to form a ketone. Let me show you this reaction. I'll show you on here while I clear the board. So we start with the secondary alcohol, which has two alkyl groups attached to it, and we form a ketone, which has the C double bond O within the carbon chain. So in this case, we have the secondary alcohol. I've got propanol. So we got so the alcohol there. Oh, look at this pen, much better. Oxidize it. So we identify our oxidizing agent as the potassium dichromate, and then we form the ketone. So H3C, and the ketone has this C double bond O within the molecule, and we lose H2O. So this C double bond O is called a carbonyl group. Within the molecule, it's called a ketone. Now, we can't oxidize any further under these reaction conditions. So these alkyl groups, as opposed to before we had another hydrogen which made the next oxidation possible, these alkyl groups prevent that. The extra alkyl group limits any further oxidation under these mild conditions. Now, our tertiary alcohol is a bit different again. Our tertiary alcohol has it surrounded by three alkyl groups. So if I do a tertiary alcohol, where we got R, and OH, now we can't actually oxidize this at all. No reaction occurs under these conditions where we warm it up with the potassium dichromate due to the alkyl groups that are around it, the other R chains. As no reaction takes place, we're not going to observe a color change. So in the primary and the secondary one, where the alcohols are being oxidized, the dichromate is being reduced. So that means we're going to see the dichromate go from the orange into the green, and that color change confirms our oxidation has occurred. Now, a tertiary alcohol, on the other hand, has no reaction occurring. So that means we're going to see no color change. So we can actually use this as a distinguishing test to identify if we have a tertiary alcohol compared to if we have a primary or a secondary alcohol. Primary or secondary, we have oxidation, we will observe a color change. Tertiary, we have no oxidation, we will not observe a color change. So we can use this to distinguish our tertiary alcohol from our primary or secondary, as these will observe color change from orange to green, but the tertiary will remain orange. And with that, we got another unit down. Very well done. What have we done today? Record the chemistry of alcohols exemplified by ethanol in the following reactions: oxidation of carbonyl compounds and carboxylic acids, dehydration to alkenes, formation of esters by esterification with carboxylic acids. Then we suggested characteristic distinguishing reactions, for example, mild oxidation right at the end there. Here are the tasks. You know what to do. Pause it, work through them, have a great time and learn lots. Thank you very much. I'll see you when we start a new unit next time. Have a fabulous day.